Hello, good morning and good afternoon to everybody. So I changed this talk a little bit to mercury cadmium telluride infrared photodetectors for imaging and sensing, which covers shortwave as well, just to broaden it a little bit to fit for the audience. And thank you very much for the introduction. So I'm from the University of Western Australia, and I acknowledge the funding agencies, Australian government, ANFF, and the Western Australian government. So this is the outline of my talk. So I speak a little bit about the application of the infrared detectors. Then I'll talk about the MBE growth of the infrared material and detectors, and a few examples of the works that we have done at the University of Western Australia. So basically, this shows the, so what's the infrared bands that we are looking at? This is the atmospheric transmission. As you can see, so we have the short wave, mid wave, and long wave, which varies from 1 micron to 13 to 14 micron. And this short wave band is very useful in different applications, as you will see shortly. But in general, we work in all of these three bands at UWA. So some strategically important application of IR detectors are in night vision, surveillance, IR homing, astronomy, remote sensing, and medical imaging. Especially for astronomy, they are all the satellites, they are equipped with short wave, mid wave, and long wave. And for Earth science observation, all of the time they use the short wave imaging and detectors. Just to give you another examples of the strengths and capability of the shortwave infrared. So it's generally used in the surveillance and security. As you can see, the difference in the imaging in the visible and using the shortwave in the fog or in the smoke, or where the visibility is limited, is very strong, and all the features can be captured. And also for the Earth observation and remote sensing. So these are all the satellites which are equipped with the shortwave and mid-wave infrared detectors and arrays for monitoring the different phenomena on the Earth. So you can see that it's still all of the satellites which are used, they are equipped with the shortwave arrays and detectors in the past, present, and future. In terms of the material that is used for infrared detection, there are several materials. I took this picture from one of the infrared detector manufacturers in France over there. As you can see, the MCT, or mercury cadmium telluride, which is we are using at the University of Western Australia. It has the capability to cover all the bands from short wave to long wave, although there are other materials such as QUIP, InGas, and INSB or Newman-Timonite. But the strength of the mercury cadmium telluride, or MCT, is that it can cover the whole band. So that's why we mainly focus on this material at UWA. And these are some of the present industry standard of the photovoltaic in the infrared. As you can see, it's a mercury cadmium telluride and type 2 superlattices. These are from Raytheon and Teledyne company. So mercury cadmium telluride is the choice for industry for high performance applications. Another motivation for specifically the shortwave effort that we are performing we are doing at UWA is for the LIGO gravitational wave detectors. I'm not going to go to details, but these detectors operate, this facility or these instruments operates at or will be operate at 2 micron, slightly greater than 2 micron operating wavelengths, and currently there are no commercially available large area 2 micron detectors which can be accommodated in these LIGO observatory. So we have a collaboration with them to basically make a prototype of this high QE shortwave infrared for this facility. And just to give you an example again, so this is the status of the commercial SWIR detectors, which you can find in the market. This data is a little bit old, from 2 years, because this field changes every year. But as you can see, most of the detectors for shortwave infrared are, they have a low quantum efficiency of below 90% at the targeted operating wavelength of 2 micron. So what do we do here? We use a photovoltaic or photodiode to create the infrared detectors. This is our typical structure that we use, a schematic of the structure that we use. So we have an MBE grown mercury cadmium telluride, and then we create the PN junction that everybody is familiar with using the reactive ion etching method. And then we do the further processing to create contacts and packaging and so on. So in terms of the experimental result that we have done on these, again, these are a little bit from last year or 2 years, more than last year. So basically, we fabricated these devices for shortwave IR applications. As you can see, this is the basically theoretical limit of the operation at room temperature for shortwave detector, and the detectors that we fabricated, they show the dark current, means that in the absence of light, a very good dark current for the intended application. The reason that we target for 200 Kelvin or 300 Kelvin is because they won't need any cooling. They can be cooled using thermoelectric or minimal cooling requirements. So how do we grow these infrared detectors and materials? So we use an MBE32P reverse system, which is equipped with these sources and the dopants, and we have several in situ monitoring instruments. So these structures or detectors are grown on the cadmium telluride substrate, which is the standard substrate for the mercury cadmium telluride detector growth, because it's lattice matched to the mercury cadmium telluride. In terms of processing the detectors after they have been fabricated, so we have an extensive clean room equipment, as you can see here, E-beam, zinc sulfide deposition. So we use all of these tools to basically process the MBE grown materials to make a detector. In order to make imaging devices for shortwave imaging, we further need several equipment for packaging and hybridizing with the readout circuits. So these are the new equipments which will come to UWA thanks to the ANFF and other funding agencies, which allows us to be in the forefront of the imaging, infrared imaging systems, especially this Philip chip bonder, which will be getting soon, hopefully. Basically, with these equipments, everything will be done in-house in the University of Western Australia, from material to the final device. These are some pictures from the test arrays that we use for assessing the quality of the devices and materials, basic devices before packaging. So we have successfully fabricated the imaging arrays for mid-wave. This is not for shortwave, but the principle is the same. So we have fabricated 320 by 260 mid-wave IR infrared detectors for imaging. Very nice uncorrected and corrected images has been produced by the array. So this is the short movie from that from the array that we made. We also have an extensive collaboration with international partners for infrared devices and materials from Japan, Germany, Turkey, and other countries. Finally, this is the most of, not all of them, but most of the main key personnel involved in the mercury cadmium telluride detectors and imaging system development at the University of Australia. And again, thanks all the funding agencies which help these products to be realized. Thank you very much.
Thanks so much, Nima, for a really interesting talk. It's amazing what these IR detectors, imaging detectors can do. I'm just looking at Slido, and yes, we have a couple of questions. First one is from Matt. What's the underlying process for the reactive ion etching type conversion?
The physics behind the
underlying process.
Underlying process is that basically the mercury cadmium telluride gluon is the P-type material. So basically, so this material that is grown is initially P-type, but for photodetector or photovoltaic operation, we need a PN junction, as everybody knows. So the RIE basically type convert this region to N by filling the mercury vacancies using the interstitial and other processes to fill the vacancies in this layer and convert it to N type. The exact physics is not known, but basically that's what everybody agrees, that the vacancies which contribute to the material being P-type is filled with the released mercury during the RIE process. Therefore, it's type converted to the N-type. If that's
awesome. Thanks, Nima. I've got a second question, and I think we move on. But this second question is actually about biomedical imaging. The question is, how sensitive is the shortwave IR detector in terms of distance, target signal strength, and is there any potential harm to the body if applied to biomedical imaging?
No, these wavelengths should not be are not harmful to the body or tissue. And in terms of the distance and other stuff, it depends on the optics that you use on these devices, basically what optical lenses and the optic system basically defines the distance that you can use on these detectors.
Awesome. Please join me in thanking Nima once again.
Thank you very much.